So this lecture is going to be about chapter 19, and its signals are transition from section 2 of the lecture of the course to section 3 of the course. You can see here a rundown of the synopsis of section parts 1, 2, and 3, and kind of what they entail and where they're going with section 3. Here are your objectives. One of the ones I want to point out to you is B. B is not going to be covered in the lecture. This is one of those things I'm going to ask you to read and study on your own. It's very definitional, very, hey, place this spectrum range with that type of, with what it's used for, and that's not really something that's easily taught, more of something you're going to need to study. So in this portion of the lecture, we're going to introduce the concept of the communication system, something that we've already kind of talked about. But what I want you to think about is you have this information, right, and you're trying to transmit it from point A to point B. And we're talking about doing this wirelessly. So we're going to take that information and we're going to give it to a transmitter. This transmitter is going to turn it into a signal that is going to be transmitted through the atmosphere. So you see that TX there, that is a typical abbreviation for transmitter. That signal is going to be sent out into a communication channel. And that communications channel is going to be anything from air to space to water, any number of mediums. So the communications medium. Then that information is going to be received by a receiver, typically abbreviated as RX, and it'll be recovered from there. One of the things that we haven't really discussed up to this point is this concept of noise, which is the other kind of key element of a communication system, and that is an interference that's introduced inside the communications channel, and it can be also introduced at the transmitter and at the receiver as well, but primarily right here on the communications channel. So these are your four portions of your communication system: your transmitter, your communications channel, your receiver, and your noise. So noise, just to give you a little bit more information about it. Noise is random, undesired energy that interferes with your signal. And it can be constructive, destructive, but ultimately it's got several sources in different categories. We're going to have external, which is going to have your industrial, which you can think of as man-made sources. This is motors, generators, and other man-made sources like that. You have your atmospheric, which is a classic example would be lightning. That's that electrical energy burst that can cause problems with signals. And then extraterrestrial. So your young careers in the military, you will hear communications people joke about the infamous solar flare and how they can affect communications. And obviously those are extraterrestrial. Then you have your internal sources of noise. And we're not going to dig into these, but you can just know that thermal noise or thermal effects and semiconductor effects can introduce noise to our signals. Essentially, the hotter it is for a system equals more noise, and semiconductors, concept being here that the types of semiconductors can affect noise as well. So in this portion, we're going to talk about the electromagnetic spectrum. So it's going to be important for us to get used to talking about electromagnetic waves and how they are mathematically defined. So the spectrum is broken up into subcategories, which you classify by our frequency and wavelength. Now I'm going to take it that you guys have been exposed to this before in your physics classes, but let's go over it again. So we have this concept of frequency, which basically is measuring how fast a wave oscillates, and it's measured in hertz. A hertz is a cycle per second, okay? And then you have wavelength, lambda, that's this Greek symbol here, there. It's the physical distance from peak to peak in one cycle of a wave, and is measured in meters. And then you have your period, which is the length of time that it requires to complete one cycle. And that's measured in seconds and is defined according to this right there. So those are going to be important ways for us to talk about individual waves. And one thing that's not talked about here yet, and we'll talk about it in a little bit, is phase. And phase is just another characteristic of the wave. So we'll get into that in a minute. So period versus wavelength. So wavelength and period are going to be measurements of one cycle of an electromagnetic wave, but the big difference here is the unit of measurement. So if we have this diagram, and it's in time, measured in seconds, and we're going to leave the vertical axis empty. We go on like that. In this case, we say, hey, we're going to measure from this peak to that peak. That's one cycle, but because we're measuring in time, we have capital T for our period. So this is capital T equals the period of the wave, and that's going to allow us to find out some other information. But then we also have, say, this wave, like that, and over here it's measured in distance, meters. And then we go ahead and say, hey, we're going to cycle to one cycle measurement of that from here to there. That's going to be lambda because we're measuring in distance. So the key things about these is these allow us to do a few different things. We can convert using period and wavelength to find frequency. So the relationship for period is frequency equals 1 over time. And then over here, for lambda from wavelength, we can say that c, the speed of light, which is 3 times 10 to the 8th meters per second, equals frequency times wavelength. So these are physical means for us to convert back and forth from those values, wavelength and period, to find frequency, which we can use later on. So using those, we'll be able to do a lot more work later on, and we can also find, for example, if we had wavelength, we could eventually get over to figuring out what the period is, or if we started with the period, we could figure out what frequency is and then find out what the wavelength is from there. So we see practice problem 19.1 here, and what they're trying to do is get us to figure out what the wavelength is for this radio station when it has this frequency of 101.1 megahertz. So you're going to want to get comfortable with the terms kilo, mega, and giga, this being 10 to the 9th, this being 10 to the 6th, and obviously 10 to the 3rd. We're going to use those pretty frequently and throughout this section of the course. So go ahead and pause the video, go ahead and work that problem using those equations from the previous slide, and when you're ready, come back and we'll work through it. Okay, so let's start by going ahead and setting up our equation, and we know that speed of light equals lambda times frequency, or wavelength times frequency, and this is then going to be able to be changed around because we're looking for lambda. Isolate that, c over f. That's going to be 3 times 10 to the 8th meters per second divided by 101.1 megahertz, which we're going to go ahead and we're going to say this equals 3 times 10 to the 8th meters per second over 101.1 times 10 to the 6th from our value right there, hertz. And a hertz, if you remember, this just equals 1 cycle per second, which typically abbreviated as just 1 over seconds. So we can cancel out, just cancel this with that right there. So now we have a unit of meters, which is going to be good because that's what we're looking for with lambda. And let me just go ahead and set this up, and we will, actually, let's go ahead and do some canceling here. Cancel that 6, and that's going to make this a 2. And that's because when you divide those powers, you're just going to go ahead and you're going to have, when you have 10 to the 8th divided by 10 to the 6th, you end up with 10 to the 8 minus 6. If you remember that from a long time ago in your math classes, it gives you 10 to the 2. Then come down here, we're going to end up having, do some quick math with the calculators. You'll end up with 300 divided by 101.1, and that's going to be 2.967, and we'll bring that meters back into play. Don't forget your units. If your units don't check out, it's going to be an indication that you probably did something wrong somewhere. Okay. So here's practice problem 19.2, and it says, what is the frequency of a signal whose wavelength is 8 centimeters? So, just like I said, you might want to be familiar with your kilos, megas, and gigas. You might want to be familiar with your centis and nanos and micros as well. So, centi, 10 to the negative 2. Micro is going to be this symbol mu. It's 10 to the negative 6th. And then you might see nano as well, which is 10 to the negative 9th. I don't think we go any further than that, but we may. So go ahead and pause the video, work that problem, and then come back. Okay, so again, we're going to fall back to our C equals frequency times wavelength. And in this situation, we're actually going to be looking for frequency. So we're going to have frequency by itself, and that's going to be C over lambda. And that is 3 times 10 to the 8th meters per second divided by 8 centimeters. And we're going to have to convert this centimeters into meters before we can actually do anything. So let's go ahead and do that now. And that's going to be 3 times 10 to the 8th meters per second all over 8 times 10 to the negative second meters. And then we do this again. The one thing I want you to remember is you're dividing again by that powers of 10, so we're going to end up with 3 divided by 8 times 10 to the 10th power in the per second, because we can cancel out the meters there. So we do some math and we end up with this equals 3.75. Actually, let's back up. Equals 0.375 times 10 to the 10th hertz. Just remember that per second there, the 1 over s equals hertz. But what we're going to do is we're going to simplify this a little bit, and we're going to change that to 3 times, or 3.75 times 10 to the 9th hertz. And if we recall from the other slide, 10 to the 9, that's going to give us 3.75 gigahertz. Okay? So with that, we're going to talk about the actual signals themselves and how they're actually going to look and how we're going to define it using mathematical expression. So I'm certain you've seen sine waves before. Obviously, we've already drawn one on the thus far. But here we go. We've got this sine wave. We're going to have time over here, and we're going to put voltage, so volts, V, on the vertical axis. So one of the things we're going to be looking at is, one, how big does that wave, or how high does that wave go up? What's the magnitude that it exceeds on that vertical axis? And we're going to call that the wave's amplitude. So amplitude. We also have been talking about, those peak to peak, that 1 cycle time in this case, our period. And one of the things that we were beginning to talk about or I had mentioned, was the concept of a phase. Now, a phase is going to be a horizontal shift in how a wave starts. So if we have this wave here, it has a phase shift of 0 if we're talking about a sine wave, but it would have a phase shift of 90 degrees if it were a cosine. And the way we're all ultimately going to start writing these out is we're going to have this concept of V, and we typically start these with sub m for the message signal, and it's dependent upon time, and it equals V sub m, where V sub m is the amplitude, because we know that sinusoidal waves have an amplitude of 1 unless they're modified, and sine 2 pi times the frequency f sub m times time plus a phase shift theta sub m. Now we'll be able to find the frequency by solving the concept, or the equation 1 over t sub m, and this, the phase shift, we determined by examining that plot and figuring out how it's been shifted according to that. Do not, forget this 2 pi. This is just a quintessential portion of how we define them when we're talking about signals. It's not always there in most other sinusoids, but when we talk about a sinusoidal wave that's defining some sort of information wave, it's going to have that 2 pi in there. So with that, let's go ahead and move forward to talking about time domain sine waves, and we're going to consider this wave with a 400 hertz frequency and an amplitude of 2 volts. We can actually see this plot here, and one of the things we can do is we can actually confirm that information. So see here, it's coming in at 2. That's going to tell us, confirm that we have a amplitude of 2 volts, and then we want to go ahead and confirm that that frequency is in fact 400. And to do that, we're going to check out what's the time from this start of the cycle to the end of the cycle. If we say we have a time here of 0.005, this halfway in between is going to be 0.0025. And we do the math, we say, okay, that if our t equals 0.0025 and f equals 1 over t, that equals 1 over 0.0025. Bust that calculator out, and that will confirm that is in fact 400 hertz. So having that information, and we can see also that there is no shift. We started at 0 at time 0 up here on the plot. That's going to be the thing to indicate to us that we have no phase shift at all. So let's work on writing that signal out mathematically. So remember, we had V sub m of t equals capital V sub m sine 2 pi f sub m times t plus theta sub m. And because we know that this, let's use a different color here. And that theta sub m equals 0, and we know that f sub m equals 400, and that capital V sub m equals 2 volts. So we're going to go ahead and be able to write this equation as 2 sine 2 pi times 400 times t, and that's going to be all there is to it. So one of the other ways that we actually work with signals is writing them outside of the time domain. We write them in the frequency domain, and this is probably going to be one of the most new methods of talking about this for you guys. So hopefully I can do it justice and get you guys spun up on how it works. So the frequency domain. So we can convert time domain signal to the frequency domain by using what's called the Fourier transform. So the way this is going to work is we're going to start, I'll show you this equation. We have f hat of psi. That's going to equal the integral from negative infinity to infinity of f sub x, our time dependent signal, times e to the negative 2 pi I x psi dx. So by conducting this integral, we're going to be able to figure out all of the Fourier transform of whatever our original signal is here. Now, I understand this is it's an integral with complex values, but we're never going to do this. Instead, what we're going to do is we're going to figure out all of our frequency information, all of our frequency domain info by inspection. And that means that you're going to be able to look at either the mathematical representation or a plot and be able to figure that information out. The biggest thing that we're doing here is we're trying to find f. Every single time we're looking for f. And by f I mean our frequency. As soon as we can find that, we can start figuring out what our frequency domain looks like. And our mathematical will be used for more complex ones, whereas our plot will be used for simple ones. Okay, so let's talk about a frequency domain and how that's going to be plotted out. And it is plotted out by a magnitude versus frequency. So you have your frequency on your horizontal and your magnitude on your vertical. So we'll have frequency, and we will have this in hertz, and we'll have our magnitude, and lots of times we'll have this in volts, just because that is what many of our waves are going to be defined as. So let's use the example of the 400 hertz with a 2 volt peak, and we'll go ahead and plot that out. So the way this is going to look is we're going to just go over here to 400 hertz, and then we're going to have plot here. It's going to reach up to 2. And that's all that's going to look like, is just this one single line at 400 hertz extending up to 2 volts. So time versus frequency domain plots. One of the things that's pretty important here is they're both displaying the important characteristics of a signal, just in different ways. And we can think about this if we had a much more complex signal. Say, for example, if v sub m of t equaled 2 sine 2 pi times 440 t plus, let's not make it plus, let's do minus 3 sine 2 pi times 900 t plus pi over 4 for a phase shift, and let's go ahead and add in 5 cosine times 2 pi 1100 t plus 2 pi over 7 for a phase shift for that one. So if we look at this, we say, hey, we can plot that out. We just got to plug it into a calculator or computer that has a graphing capability. We can actually see what it looks like. But based on what we see here, this is going to be a complex signal. And one of the ways that we can actually do that and break it down to a simpler way, here we have that same signal, is we can plot it. And you see here we have the time domain, and we've got it's got that max voltage when you start adding those composite signals together. This is kind of how it looks. It's still periodic in nature in that it repeats itself, but if we want to get a quicker glimpse at important information about that signal, we plot it in the frequency domain. And if we have this over here, frequency in hertz, and we have here's 1100, and there's 900, and then we've got 440 over here. Then all we have to do is plot out the magnitude. And mind you, we're going to do the absolute value of the magnitude, which we should see back here on this slide in the frequency domain. So the absolute value of that magnitude. And then we just go ahead and say, okay, this is 1, 2, 3, 4, 5. And we can plot all those signals. 2, and this is 3, and 5. And that just gives us all the same information, and it's a lot simpler. It's a lot easier to digest, and you're not trying to figure out what the frequency is from this plot here. So it's going to be a lot more difficult for you to extract the frequency from this plot. So more difficult to find F. And in this one, in the frequency plot, we'd actually say that this has 3 frequencies. So it'd have an F sub 1, an F sub 2, and an F sub 3. And we'll talk about that some more as we go on. One of the important concepts is talking about bandwidth, and bandwidth is how much of the frequency spectrum is being occupied by a signal. So if we go back to our previous example here and we talk about how much bandwidth this actually takes up, we can see that it's spread from 1100 frequency or 1100 hertz to 440 hertz, and this is going to be its bandwidth. And the way we'd figure that out is we'd say, hey, what's 1100 minus 440? And do that math. That's 660 hertz, and that equals the bandwidth of that signal. So another example here, pause it real quick, go ahead and work through that, and then come back and we'll work through it. All right, so in this case, fairly simple. Bandwidth is going to equal that F1 minus F2, where F1, so in this case, if we're using this equation, F1 is greater than F2. So this is going to be 3,000 minus 300, and that equals 2,700. Now, hertz. Okay, so we have this practice problem here, and this is going to be designed to let you use this plot to try and figure out the information about this signal. So I want you to use the plot and find the mathematical expression. Horrible handwriting there. So what I'm going to also add to that is that this is in time, seconds, and this is in volts. So just keep that, the horizontal is in time and the vertical axis is in volts. Go ahead and pause the video, work through that, and then come back and we'll talk about what it's going to be. Okay, so what I want you to do when you're working these is start by remembering your expression. The general expression is V sub m of t equals capital V sub m times sine 2 pi times f times time plus theta sub m there. So we need to figure out what each one of these things are before we can move forward. One of the key things we can start off with is we can see at time 0, we start at 0. So that is an indicator for us that our theta here, theta sub m, equals 0. Then we're going to go ahead and figure out what's the next kind of simplest thing to find. Let's go ahead and with capital V sub m, and that's figuring out what that amplitude is. If we see right here, let's just go ahead and assume that it goes up to there, and we do some quick counting. So that's 1, 2, 3, 4, 5. So it's 5, and that's out of 8. So it's 1 5/8. Capital V sub m, 1 5/8. Now we're gonna have to do we're gonna have to find the period of this in order for us to find the frequency. And the way we're going to do that is we can either start here at 0 and go till we go back to 0, which is right here at 0.5. So that's pretty easy and convenient. So that right there, that equals t. So t here equals 0.5 seconds. So now that we have that, we can say frequency equals 1 over capital T, which equals 1 over 0.5 seconds, which equals 2 hertz. And now we have all the ingredients we need to make this equation. And if we just go ahead and we'll just stick with this, just write it right here on the plot. So that's going to be V sub m of t equals 1 5/8. You can figure that out if you really want to. I think it's like 1.625, something like that. Yeah, it seems right. Times sine of 2 pi times 2 times time plus 0. Just close that out. And that is going to be our final expression. Now moving on, so this is the portion of the electromagnetic spectrum and how it's broken up from extremely low frequencies to extremely high frequencies. And I'm not going to go through this and read all these things to you. I know that you're smart, can read, but go ahead and pause this if you need to, read through those, make yourself some notes, maybe some flashcards. I don't intend on testing you a lot on this because I feel like this is stuff you can just look up if you really need to know it. But in most cases, we're not going to really need to know it. And then another interesting aside that kind of goes with that is, so you just seen all of this right here. It's talking about where those frequency bands are and what we use them for. But kind of interesting to go with it is that there's only so much spectrum, and we can't buy any more. We can't expand it into multiple dimensions. It's one frequency spectrum that we have. So the FCC kind of controls all that. Make sure if you're allowed to be communicating on it, you can. If you're not, you're heavily penalized, so on and so forth, and controls it very strictly. So when there are bands that are available, they go on for sale for people to say, hey, this is my frequency band, this is what I'm going to own, I'm going to put all my communications and stuff on it, and that can actually get pretty expensive. 400 megahertz spectrum was auctioned for $44.9 billion. So that is pretty valuable asset, and it's one of those things it's governed throughout the world. FCC does it here in America, so just be aware of that. And let me know if you have any questions in the forum or via email, and I will get back to you as soon as possible. Good luck. I hope you're having a good day.